In this lesson, we study the fundamental theorem of calculus. Here's what it says. The fundamental theorem of calculus says that if we have a function f and we know it's continuous on the closed interval from a to b, then capital F of x equals the integral from a to x, where a is your lower limit and x is your upper limit, of f of t dt. And this function is continuous on the closed interval a to b as well, and differentiable on the open interval from a to b. And its derivative is f of x. Now, what's really important is capital F of x is the function whose derivative is f of x itself. So capital F of x is what we will call the antiderivative of f of x. Because when we take the derivative of capital F of x, we get f of x. Now, just before we look at a couple examples, I want us to notice that x appears in the as the upper limit here. In some of these examples, x will be the upper limit. Other times, it'll be the lower limit of integration. What's really important is that the independent variable is x, okay? And t is just like a dummy variable. It's a dummy variable, but y will be dependent on this independent variable, x. So let's remember that. So anyway, when we find the derivative of this integral, notice that it's just f of x, f of this upper limit. Okay, everybody, here is our first example. Use the fundamental theorem to find dy dx, that is the derivative of y, with respect to x. If, here's your first one, if y is equal to the integral from a to x, t cubed plus 1 dt. All right, according to the theorem, the fundamental theorem of calculus, it says that dy dx, the derivative of y with respect to x, will be the derivative of the integral from a to x of t cubed plus 1 dt. And remember, the theorem says that this is equal to the function evaluated at this upper limit. So then it's simply x cubed plus 1. I'm basically evaluating this function at this upper limit. So this here is dy dx. Okay, cool. Let's do another one. Find dy dx if y is equal to the integral from x to 5. Notice that x, your independent variable, is the lower limit of integration. Your function is 3 times t times sine of t dt. I don't need parentheses around my integrand because it's all one term. You can put parentheses if you want, but because it's one term, I don't need parentheses. All right, so according to our theorem, dy dx is equal to the derivative of our integral. Or actually, yeah, I mean, this is good, except what I was thinking of right now, and I guess I can do it in the next step here. Let me finish writing this out. What I was thinking is in the fundamental theorem of calculus, it's the upper limit that is the variable of integration. And so the upper limit is your independent variable, x. So I want to swap these limits. But remember from an earlier lesson, we can do that. But what that would mean is we would have dx, right, of the negative of, and then your limits will go from 5 to x, okay, 3t sine t dt. All right, now this negative we can just factor out. Let me move this up a little bit. So it's the opposite of the derivative of the integral from 5 to x of 3t sine t dt. All right, very good. So then this is equal to the opposite of, now remember all we need to do is evaluate our function at this upper limit. So then this is 3x sine x. And it's the opposite thereof. So very good. All right, cool. Now let's look at another one. Now this next one is interesting. I like it. You're going to see that y is equal to the integral from 1, watch this, to x squared of cosine of t dt. So what's different here is your upper limit is x squared, not x. So what this means is that y is basically a composition of two functions. So this is going to require the chain rule. So let's do it. dy dx is equal to d dx of the integral from 1 to x squared cosine t dt. Now, according to the fundamental theorem of calculus, this is equal to, all right, here we go. So it's equal to cosine of x squared, and then we must also take, remember the chain rule, we must also take the derivative of the inner function, right? And the inner function is x squared. And so then this is times 2x. We should write it with the 2x, if I can just move this up, with the 2x in front. So 2x times cosine of x squared. So this is like a good little review of the chain rule. Okay, so very good, everybody. All right, let's do maybe one more. What if y is equal to the integral from 1 plus 3x squared, look at that, to the power up to 4 of 1 over 2 plus t dt. All right, so let's do it. So this is dy dx is equal to d dx of the integral from 1 plus 3x squared to 4 of 1 over 2 plus t dt. All right, so there's a few things that we're going to do here. First of all, we want to swap these limits of integration. What that's going to produce is a negative sign. So let's go ahead and do that first. Okay, so then this is going to be the derivative with respect to x of, all right, so let's say the opposite of the integral from 4 to 1 plus 3x squared of 1 over 2 plus t dt there. And then we can factor out the negative, and just like the previous problem, we're going to need the chain rule here. But let's just hold off on, let's just factor out the negative first. So then it's the negative of the derivative with respect to x of the integral from 4 to 1 plus 3x squared of 1 over 2 plus t dt. All right, be careful. My t right here, in my opinion, looks like the plus sign, so be careful. All right, so here we go. We're going to need the, we're going to evaluate our function at this upper limit 1 plus 3x squared. So this dummy variable t gets replaced with 1 plus 3x squared. Move up a little bit. And then we're also going to need to take the derivative of that upper limit with respect to x, because this is the chain rule. All right, so then it is negative, and then we have 1 over 2 plus, now here we go, I'm going to replace this t right here with this upper limit. So it's 2 plus 1 plus 3x squared, okay, times, and then what we need to do is take the derivative of the upper limit 1 plus 3x squared, because this is the chain rule. So now it's just some simplifying, right? So then it is negative 1 over 3 plus 3x squared, all right, times the derivative of 3x squared is 6x. So if I continue simplifying, I think we're just moments away, then this is negative 6x over, if we factor out a 3 from the denominator, we have 3 times 1 plus x squared. So then it is equal to negative, and then we have 2x over 1 plus x squared. Awesome. Good job, everybody. Now, before we move on to the second part, there is a second part of the fundamental theorem of calculus. I want to go back, if I can. So, again, I don't mean to make you dizzy, but I do want to take you back to what the fundamental theorem of calculus says. And I just want to make sure you understand what the theorem is saying. If I can find it, I think we're close. Here it is. All right, here's the fundamental theorem of calculus. All right, so allow me to try to rephrase this for us. So if we take a function and we integrate, right, this is the integral. If we integrate the function and then differentiate, this is our differential, right? If we integrate the function and then differentiate the result, you get the function back again, the function f back again. Isn't that pretty amazing? So again, if you integrate your function f and then you differentiate the result, you're right back to where you started with function f again. Now, let's go back. Let's actually now go to the second part of the fundamental theorem of calculus. It's pretty fascinating. Now, this is the second part of the fundamental theorem of calculus, and it deals with how to evaluate definite integrals without having to calculate limits of Riemann sums. Not too long ago, you and I were finding limits of Riemann sums, right, which required us to draw or construct rectangles, right? And so although it was fun, it was very time consuming. And so instead of having to calculate limits of Riemann sums, instead we can use this theorem of calculus, which says that all we have to do is find and evaluate an antiderivative. That's what capital F stands for, is an antiderivative. All we need to do is find and evaluate the antiderivative, or an antiderivative, at b and a, which are the upper and lower limits of integration. Isn't that pretty amazing? Like, for example, what if we want to evaluate the integral of cosine of x from 0 to pi? So all we need to do, according to the fundamental theorem of calculus, is find an antiderivative for cosine. Okay, let's remember what that means. That means I want to find a function whose derivative is cosine. To find an antiderivative for cosine means find a function whose derivative is cosine. So in other words, find a function such that when I evaluate the derivative of that function, I get cosine of x. So what would this be? This would be the antiderivative of cosine. Well, that's sine of x. So sine of x is an antiderivative for cosine. So let me make room here. Let me get rid of what I wrote just because I need the space. So an antiderivative for cosine is sine. So all I have to do, according to the fundamental theorem of calculus, is take that antiderivative and evaluate it at my upper and lower limits of integration. And the notation for that is from 0 to pi. Okay, which means this is equal to sine of pi minus sine of 0, which is 0 minus 0, so the answer is 0. Isn't that amazing? All right, cool. Let's look at another one. Let's look at the integral of secant of x times tangent of x dx from negative pi over 4 to 0. So again, what we want to do is find an antiderivative for secant of x tangent x. In other words, find a function whose derivative gives you secant of x tangent of x. Again, I can write it like this if it helps. The derivative of some function gives me secant x tangent of x. So as long as you know your derivatives really well, then you'll remember that the derivative of secant of x is equal to secant x tangent x. So an antiderivative for secant x tangent x is secant x. So we will use secant x. So then this is secant of x. That's the antiderivative, evaluated from negative pi over 4 to 0, which means secant of 0 minus secant of negative pi over 4, which is equal to 1, right? Secant of 0 is equal to 1 minus negative pi over 4 is in quadrant 4, and secant is positive there, and it is root 2. So then this is root 2. This is an exact answer. Pretty cool. Let's do another. This time around, let's evaluate the integral of 3 halves root x minus 4 over x squared. Let's put parentheses around this integrand, dx. And our lower limit will be 1, our upper limit will be 4. Okay, very good. So this is equivalent to the integral from 1 to 4 of 3 halves times x to the power of 1 half minus 4 times x to the power of negative 2. Okay? So then we know that an antiderivative will be 3 halves times x to the power of 1 half plus 1 over 1 half plus 1 minus 4 times x to the power of negative 2 plus 1 over negative 2 plus 1. Okay, so all of this evaluated from 1 to 4. Of course, I'm going to simplify this a lot. All right, so then this is equal to 3 halves times x to the power of 3 halves over 3 halves. I'll simplify even more in the next step. Minus 4 times x to the power of negative 1 all over negative 1. Let's put parentheses around all of this from 1 to 4. You can see we still have a lot more simplifying to do. This 3 halves here will divide out with this 3 halves here, and you're left with just x to the 3 halves plus, right, because of the two negative signs there, 4 over x. So there's an antiderivative, and that's being evaluated from 1 to 4. Cool. I think we're ready now. So then this is equal to 4 raised to the power of 3 halves plus 4 over 4 minus 1 raised to the 3 halves plus 4 over 1. So remember that this means the square root of 4, which is 2, and 2 cubed is 8. So then this is 8 plus 1, so this is 9. So this is 9 minus, and of course, the square root of 1 is 1, and 1 cubed is 1. 1 plus 4 is 5. So this is 9 minus 5. So the answer is 4. Isn't that great? Now this next example is really important. We want to consider two functions. First, f of x is equal to x squared minus 4. and g of x is equal to 4 minus x squared. Now, these are mirrored images of each other. The graph is a parabola, correct? And what we want to do is we want to compute the definite integral of each of these functions from -2 to 2. And then after that, we want to compute the area between the graph and the x-axis over that same interval from -2 to 2. Now, the idea here behind this example is area is always a non-negative quantity. Area is always a non-negative quantity. What we're going to find is that the definite integral from -2 to 2 is going to give us a negative value. But when we are talking about the area between the graph and the x-axis, because the area is always a positive value, we want to make sure that we are giving a positive response or positive answer. Okay, so let's first look at a picture. I think that'll help us a lot. So here's the graph of f. It's this parabolic curve here, and we're asked to evaluate or compute the definite integral of this function from -2 to 2. So all of this region. And then also over here for g. All right, so let's do that now. So let's answer part A together. All right. So let me move this up. All right, so this is what we are asked to do in part A. The integral from -2 to 2 of f of x dx. Okay, so this is the integral from -2 to 2 of x squared minus 4. So what we need to do is we need to find an antiderivative for x squared minus 4. So that's x cubed over 3 minus 4x. And we need to evaluate this from -2 to 2. All right. So then this is equal to 2 cubed over 3 minus 4 times 2 minus -2 cubed over 3 minus 4 times -2. So then this is equal to, so this is 8/3 minus 8. And 8 is 24/3 minus, and this is -8/3 plus 8, which is plus 24/3. So then this is negative, what is this, 16/3, and this is minus 16/3, which is equal to -32/3. That's the value of the definite integral for f of x. All right, let's do the same thing, but this time for g of x. So we just found the definite integral of f of x, right? So we just did the definite integral for this function f. Notice that, if we would have done, a Riemann sum, the rectangles, right, would be down here below the x-axis, right? And so these function values would be negative. Whereas over here, we would have constructed rectangles that are above the x-axis. That is to say, the function values that determine the height of these rectangles are positive. So what we're going to get is the same answer for g, except it will be positive. So the only difference is the sign. Okay, so let's show that now. So I'm going to get the same answer. All right, this is still part A. So we're going to do the integral from -2 to 2. This is the definite integral of g of x. And hopefully we can show that this is the same answer. So this is the definite integral from -2 to 2 of 4 minus x squared dx. All right, so then this is 4x minus x cubed over 3 evaluated from -2 to 2. That's an antiderivative. So then this is 4 times 2 minus 2 cubed over 3. A lot of this arithmetic we've done already. Let me make that a little neater. So all of that minus, and then 4 times negative 2 minus negative 2 cubed over 3. Very good. So then this is 8 minus 8 thirds, and this is going to be positive 16 thirds. Minus, this is going to be negative 8 minus, actually it's going to end up being a plus because this is going to be negative 8 thirds, and then minus a negative 8 thirds is a positive 8 thirds. So this is negative 8, which is negative 24 thirds plus 8 thirds. So that is a negative 16 thirds, but then this negative in front make it a positive. So a positive 16 thirds. So then if my arithmetic is correct, this is positive 32 thirds, which is our what our gut was saying, right? Our instinct was saying, well, we're going to get the same answer, but it'll be, because this region is, if I can go back, this region there it is. This region here for function g is all above the x-axis. All right, now notice that in both cases, the area between the curve, in both cases, the area between the curve and the x-axis for both of them, between the curve and the x-axis, is 32 thirds square units for both of them. Remember, because area is always positive. So although the definite integral of f was negative 32 thirds, here, I'll show you. You remember this is what, yeah, it's right there. Although the definite integral gave us negative 2 thirds, when we talk about area, we say the area is 32 thirds square units because area is always positive. So make sure you have this in your notes, that area is always a non-negative quantity. It doesn't make sense for area to be negative, right? So area is always a non-negative quantity. Okay, so check out this next example, to another very important example. We want to compute the definite integral of our function sine of x from 0 to 2 pi. Now, I've drawn us the picture of the graph of sine of x. Now, I hope you see now that the definite integral is going to give us 0. And the reason is because this area here and this area here match, if you will, except, of course, that this portion or this region is above the x-axis and this region down here is below the x-axis. That is to say, this region is positive and this region's negative. So they're going to cancel each other out and we're going to get 0. The definite integral is going to give us 0. But if we're talking about the area between the graph of our function and the x-axis, what we're going to have to do is we're going to have to take the absolute value of this area, because this area is going to give us negative. So if we're talking about area, folks, we got to negate what we're getting here, or that is to say, get the absolute value of this area, because area is always non-negative, okay? So we're going to do this. We're going to first consider the definite integral from 0 to 2 pi. We're going to see how this is 0, because this will give us, this is positive and this is negative, so we're going to get 0. But then after we do that, we're going to consider, okay, wait, but what's the area between the graph? And that has to be positive. All right, so let's do it piece by piece. Let's evaluate this integral. All right, so what we need is an antiderivative for sine of x, and that is negative cosine of x, right? So remember, you want an antiderivative, and negative cosine of x is an antiderivative for sine. So this is evaluated at our endpoints or at our limits of integration. So then this is negative, and it is cosine of 2 pi minus cosine of 0. So then this is negative, and then cosine of 2 pi is 1. Cosine of 0 is 1. So then this is 0. as exactly as we would have expected it, right? Because the portions of the graph above and below the x-axis cancel. Their contributions cancel each other out. Now it's time to talk about the area between the graph of our function sine of x and the x-axis over the interval from 0 to 2 pi. This is calculated, listen carefully, this is calculated by breaking up the domain of sine of x. Instead of from 0 to 2 pi, we're going to break it up into two pieces, two subintervals, if you will. We're going to evaluate the integral from 0 to pi, and then from pi to 2 pi. Okay, and from pi to 2 pi, this part is non-positive. It's not positive. So we're going to take the absolute value of that part. All right, so let's do it now. All right, so here we go. So we're going to do the integral from 0 to pi. And notice that pi is the x-intercept, or the 0 of our function. That's really important. We'll probably write that down in just a second. From 0 to pi, excuse me, of sine of x dx, right? So let's do that part first. So then this is negative cosine of x, evaluated from 0 to pi. So then this is negative cosine of pi minus cosine of 0. So then this is negative, and then cosine of pi is negative 1 minus cosine of 0, which is 1. So then this is negative 2, and then the negation of that. So then this is positive 2. So the area of this region here is 2. All right, now let's work with this piece here, okay? And we're going to go from pi to 2 pi. Now, we're going to get negative 2. But because we're talking about the area, and you and I know that area is always non-positive, we're going to end up taking the absolute value of this contribution. All right, so let's do that now. So now I'm doing the integral from pi to 2 pi of sine of x. So then this is negative cosine of x, evaluated from pi to 2 pi. So then this is negative cosine of 2 pi minus cosine of pi. So then this is negative, the negation of 1 minus negative 1. So then this is negative 2. Now, as far as what we're talking about right now, the question that we're considering is area. And so we know that area is non-positive. So what we're going to do is we're going to say the area is the sum of the absolute values of these quantities. All right? So we know the total area is 4. So notice I'm going to summarize what we did here. So notice that we broke up the domain, right? The domain from 0 to 2 pi into two subintervals. And we went from 0 to pi. We stopped at pi because this is an x-intercept. This is the point at which the graph went from above the x-axis to below the x-axis. This is a 0 of the function. So let me give us a little summary or a little plan of action, all right? All right, folks, this is our plan of action. So it's going to be important for us to find the zeros of the function so that we can subdivide our domain, or the interval that we're considering. We'll integrate the function over each subinterval, and then we can add the absolute values of those contributions. So for example, okay, find the area of the region. Stop right there. Once they say find area, we know we need a non-positive, excuse me, we want a positive answer, right? Because area is always negative, okay? So find the area of the region between the x-axis and the graph of this cubic polynomial function, x cubed minus x squared minus 2x, over this interval from -1 to 2. Okay, the first thing we want to do is find the zeros of this function, all right? So let's work on finding the zeros of this cubic function. Now, the first thing I'm going to do in order to find the zeros, which are the x-intercepts of the graph, is factor. I'll factor out an x, and that gives me x squared minus x minus 2. And then this factors further as x minus 2 times x plus 1, right? So we can see now that the zeros, which are going to subdivide our interval, are 0, 2, and negative 1. Okay, to give us an idea of what the graph looks like, I'm going to draw it really quick like we do know it goes right through the origin because 0 is an x-intercept or a 0 of the function. And we know the end behavior because it's a odd degree with a positive leading coefficient. We know the end behavior. And so if this is negative 1 here and then this is 2, then the function is like this. This is the end behavior. And okay, I could have done better than that. Hold on, folks. Something like this, okay? So there's a 0, another 0, and a 0, right? The x-intercepts. So they're asking us to find the area of these regions, folks. All right. So please see that we have two subintervals here, right? So we have the interval here from -1 to 0, and then we have the interval from 0 to 2. All right, so let's do that. So let's evaluate these integrals. The first integral will be from -1 to 0 of our function, which is polynomial, which is convenient. Okay. All right, so we need an antiderivative, so this will be x to the fourth over 4 minus x cubed over 3 minus x squared. And all of that evaluated, this is how the book writes it, like this in brackets, and then the lower limit here and the upper limit there. So this will be equal to, we have some arithmetic to do. Plugging in 0 is convenient because then you just get 0, minus, and then you get, when you plug in -1, you get 1/4 plus 1/3 minus 1, which is 0 minus -5/12. So you get 5/12. All right, 5/12. All right, so this is this contribution right here. Okay, so I can label, I think I can label this here, this contribution for this area, that area there is 5/12. Okay, that's the area for that region. Now let's go for the second. So we're going to go from 0 to 2. Now, the integral is going to give us something negative because of where this lies below the x-axis, but you and I know we're going to take the absolute value of this amount, okay? Because we're talking about area. All right, so let's do it now. Now we're going to go from 0 to 2 of our function. We expect a negative answer, but we'll negate that. We'll take the absolute value thereof. So 0 to 2 of our function, and we can use the same antiderivative, but this time it's, of course, being evaluated at different limits here. X to the fourth over 4 minus x cubed over 3 minus x squared. And then brackets and then our limits here. So then this is 2 to the fourth power over 4. 2 to the fourth power is 16 over 4, so that's 4. Minus 2 cubed is 8, so this is 8/3 minus 4. Okay, so all of that minus 0. So then this is going to be -8/3. Now, we know that area must be non-negative. Therefore, the total enclosed area, well, let me real quick, like, go to our picture really quick. Now, we got -8/3, but we know area is non-negative. So we're going to say the area of that region is +8/3, the absolute value of -8/3, right? Because area is always non-negative. So, final answer is the sum of the absolute value of the contributions, right? And so the total is 37/12. 37/12 is the total area of the region between the x-axis and the graph of our function.